very good morning to one and all. I hope yesterday was very fulfilling session with new insight emerging and enough knowledge was shared to keep enlightened mind like you to ponder upon. Today we shall continue with the second day technical session. Our first speaker is Dr. Firaj Gudar. First of all, I would like to invite Dr. Meenu Sharaf Madam to welcome him with flower and memento. Thank you, ma'am. Now I would like to give little introduction about the sir. Dr. Firaj Gudar, who is the Assistant Professor in Department of Bioengineering at Imperial College London. Prior to his appointment at Imperial, he was a research fellow in the group of Professor George M. Whiteside at Harvard University in the Department of Chemistry and Chemical Biology. He has a PhD in Microsystem Engineering from the University of Freiburg, Germany, and a BSc in Computer Engineering from the University of New Brunswick, Canada. Over the year, his achievements have been recognized through numerous awards such as UNB Class of 1939 Scholarship, Anne Mills Brown Scholarship, Governor Thomas Creighton Scholarship, and KU Leuven International Scholarship. Most recently, in 2018, UNB Young Alumni Achievement Award. Firaj and his team work in the interference of material science, electronic chemistry, and biology. His group focus on the development of new material, fabrication of low-cost sensor with the eventual aim of transforming the device developed into a fully functional portable system which is used in the healthcare, agriculture, and the food science. In addition to his peer-reviewed paper, he is an inventor of multiple patents, many of which have been licensed to commercial companies. His research at Imperial is sponsored by the Wellcome Trust, EPSRC, BBSRC, and etc. For more information on Firaj and his research activity, I would like to invite you, sir.
I will speak to the microphone. Thank you for having me. It's a great honor to be here, really. Since we came, we've been constantly eating a lot of good food. We've been well looked after. I even gained probably some weight. So, yeah, great honor to be here. So, I'd like to talk about some of our work. So, by the way, I put Indian National Conference on Microbiology and Biotechnology because the long title didn't fit, so I shortened it a little bit. Yeah, today I will just go over some of our work on low-cost sensors that we develop in my lab, predominantly using fabrics because these are inexpensive materials with actually remarkable properties. So, and it's kind of also a fitting topic because I found out that Gujarat is actually an important place for fabrics and textiles, so it kind of worked out nicely. So today I will cover some of our work in electrofluidic transducers. A transducer is just actually a short word for the field of, or for sensors and actuators. So when you talk about sensors and actuators, you can just combine them into one word called transducers. So we'll talk about some of our work on electrofluidic transducers, and in the first part of the talk and the second and the last part of the talk, we'll go over our work on gas sensors for monitoring spoilage of food. So I'm not really a microbiologist, but I had the honor of working with few. Of course, very interesting field to be in. Very exciting at the moment, especially with development of like developments in synthetic biology. The field of especially microbiome is a very it's an uninvestigated field, really. It's relatively new, and we carry a lot of microbes in our body, as much as a couple of kilos of microbes and they're kind of like actually even one of our biggest organs. So, and we know little about it. So it's a very exciting time to be working in the field of microbiology, actually. So good times really are ahead of you. So fabrics, I like to start with fabrics. What are they? Fabrics are materials that are just made of long and short fibers. So the fibers can be synthetic or natural, and the material itself can be woven or non-woven. So woven fabrics would be, textiles like the shirt that I wear. It's made of woven fabrics, so ordered array of threads really. And non-woven fabrics usually they consist of fibers that are randomly bonded together. They could be chemically bonded, thermally bonded, or mechanically bonded. So an example for non-woven fabrics is, for example, paper that we use every day. So fabrics for high-tech transducers. Why do we think that this is a good material to build transducers? Well, first and foremost, if we want to build low-cost devices, we need to use low-cost materials, and fabrics are just perfect for that. They are very, very inexpensive. Essentially, almost they're near zero cost. You can buy a ream of, copy paper for almost nothing. And if you look at a single piece of copy paper, we can produce, hundreds, thousands, or like a large number of sensors. So eventually, the net cost of a single sensor becomes negligible. So they are very inexpensive. So fabrics have 3D structures. So they are not planar. So they don't have a smooth and flat surface. They have a 3D surface, so having a lot of surface is a very good thing for building sensors in particular, because if we have a large surface area, that means we can interact with whatever we were trying to interact with quite a bit more than if we have just a flat surface. So a large variety of fabrics are actually hydrophilic, cotton textiles and paper and so on. Hydrophilicity is important because if we're trying to build microfluidic devices, you don't require pump and so on. I'll talk about this in a minute. But for example, if you spill water, what do? You take you take tissue paper and you wipe it. So a good majority of fabrics are actually they're used for interacting with liquids. And given the fact that most of our samples are in liquid phase, so that's a very good thing. And infrastructure for manufacturing for fabrics, they're already available. We can produce like gazillion T-shirts with the same pattern on them. So if we have an idea in the lab that works well, it's kind of easy to scale it up because the factory is already there. We already have the infrastructure. So fabrics are flexible, printable. You can wear them. They will conform the surfaces. Again, we can print on them easily. We can recycle them, and if we don't want, we can also get rid of them very easily. So they're easy to dispose. For biological applications, you don't want to carry around your waste. You can just essentially burn it. And they're easy to get rid of, really. And there's a huge opportunity for innovation, for doing work with fabrics. And for example, I visited a paper factory in the United States. And this factory was essentially, they were going bankrupt because they lost a lot of their business so they make copy paper for printing and so on. And because things are going digital, there's no more, or the demand for copy paper has decreased. I don't know if you've ever seen a paper machine, but these are huge machines. Some of them as long as half a kilometer. So this factory that we visited, the machine was probably about like 300 meters. And they were asking us that, like, if we had ideas to try. And I'm like, what do you mean ideas to try? Try where? He's like, try here. He was pointing at the big machine. So, and it's very unusual for a commercial facility to just try academic ideas. Academic ideas are kind of out there. They're most of them are not really well established. So they're in such desperation that they were willing to actually try academic ideas in their main manufacturing line. So because historically it's been a low value, high volume business, and now they're losing the volume, they're really losing their entire business. So they want to move away from this. So I believe that if we can come up with interesting solutions, everything is kind of ready to really get the ball rolling and then bring the technologies out there. So I would like to move on to So why or how we use these devices? So there's been an interesting development in the field of diagnostics and testing. So things are kind of moving more towards point of need analysis. So point of need analysis, it just means that doing rapid diagnosis in the field. So you don't need to take a sample and then send it to the lab. So you just take your sample and then you do your analysis right at the spot. Usually these tests, they require disposable devices. You run your test and then you throw your device away. So they need to be inherently inexpensive. And the reason why we think this is quite useful is because usually with centralized labs, you need to move your sample around. So it takes time to send the sample. You need to prep it up, package it properly so that your sample stays intact. However, some samples are also time sensitive, that if you kind of leave it lying around for a while, the sample is actually no longer good. So there are huge advantages in running the tests right at the spot, because you also don't need big machinery that tend to be very expensive. So the field of microfluidics, so by the way, for the point of need analysis, there are already existing devices that we may all know. One of the well-known examples is the pregnancy test. So this is a colorimetric pregnancy test that gives essentially 2 lines when the person is pregnant and just gets a 1 line, or produces a single line when the person is not. By the way, I found this thing on Amazon, this picture. This is a prank pregnancy test. So if you have some friends that you want to prank, this is an interesting one. But so this is a known example that's already available. It's inexpensive. It provides a quick way to know whether a person is pregnant or not. And another known example is the electrochemical glucose test. And diabetes is on the rise. So this really it's been an important step in improving the condition of diabetics. So they gave them control really over and immediate feedback about their blood sugar, and it made treatment much more effective. And I'm very lucky, by the way, to say that I'm a very close collaborator of the person who invented this technology. It's he's an incredible person, and then he recently actually his wife is Indian, and then he recently told me that he's applying for Indian citizenship. He's not from India, by the way. He's a British person, and so he's very interesting. But yeah, so but one of the things about these point of care devices is that, so normally we don't want to run a single test. If possible, we would like to run a lot of tests at the same time. So that's kind of what the field of microfluidics enables. So on the right-hand side, you see a conventional microfluidic chip that consists of various channels. So you can introduce a sample. That single sample can get divided into like multiple smaller samples, so you can run many tests at the same time. So as you see, these devices are small, but what you don't usually see is that there is a lot of machinery that are hooked up to such devices, pumps and so on, to move the liquids around. And what we have been kind of trying to do is move from such devices, although they look small, they require all kinds of like pumps and so on to move the liquids around. So we would like to go to printed microfluidic devices. And for example, through printing, we can produce very inexpensive, small and portable devices by just simply, for example, if you take a piece of paper, which is hydrophilic, so if you put a drop of liquid, what happens? It just wicks. So what we try to do is that we print hydrophobic barriers on paper and then create channels. Essentially, we have areas where liquids are not allowed to go, and then areas where liquids are allowed to go, and then we can create channels. If we introduce a drop of liquid, it can essentially split into various smaller samples and then go to certain testing areas, and then we can run a test. So we can do this through wax printing, and that allows us to eliminate pumps. So this is a small printed microfluidic device. A simple sample is added here, and then it goes and then splits into smaller samples, and it goes to the testing area, and it allows us to run multiple tests at the same time using a stamp size device, really. So, but one of the issues that you might immediately notice about such devices, although they are simple, we sacrifice or we trade in simplicity with kind of accuracy. So this is a colorimetric test. So as you see, depending on the test, it produces some sort of a color, and then from the color you can tell like kind of the concentration and whether you have your analyte in the solution or not. But for example, given the fact that 1/8 of the male population is, for example, colorblind, how can you read such a test? It consists of, you know, green and red and so on. So it's essentially kind of impossible, and it's also not very quantitative. It's just a qualitative test. It gives you an idea. But if you want precision, then you need to move away from actually just simple colorimetric. And that's why we have been kind of focusing on developing electrochemical devices. So, and by creating electronics and fluidics on the same substrate, essentially, you know, we're working in the field of electrofluidics, and that's basically just what it means. So this is one of the early prototypes that we have produced of an electrofluidic device. This is a very, it's a simple device that allows people to, so the way it works is that this is a device that you fold, and you see there are these marks here. So when you fold, this goes underneath this area. As soon as you add a liquid sample here, device get automatically activated, and this runs a PCR amplification thermal cycle. So it essentially has these like printed heaters, so these are the bluish area. It consists of conductors, so semiconductive organic material, and then this is just paper, and the yellow area is the wax where we create the barrier. So as soon as you add a liquid, the chip automatically detects it, and then it runs a temperature program. So, but the problem is with such devices is that, as I mentioned, we're using an organic conductor here. With organic materials, we develop many of the tests that we need to do. So for those, we usually require metallic structures. However, there are no metal inks that are designed for 3D materials, which, you know, fabrics are. There are some conductive metal inks that are designed for 2D materials, polymer substrate that's flat, or inks designed for this. But there are these inks, they don't really work well with 3D materials, because the way conventional commercial inks kind of work is that they have metal particles inside a polymer, and then there's a bit of solvent. So when they're printed on a substrate, they fill the pores. So the water-loving or liquid-loving 3D fabric actually becomes hydrophobic. So it no longer allows liquids to move. And I'm going to show you what I mean by this. So for example, this is a commercial ink that's used in making printed electronics. But if you try to make electrofluidic devices with this thing, you print it on a piece of paper, you see liquids can no longer go inside because they block all the pores. And we don't want that. And we would like to produce substrates that essentially act like fabrics, but have metallic structures. That's exactly what we want to do. So we have decided to develop a process that would allow us to do this. And this is kind of like what we ended up coming up with. So on the right-hand side, this is the commercial ink. On the left, this is what we develop. So if we add some liquids, as you see, it wicks all the water that we introduce, and it's fully metallized in this case. So how does it work? It's a two-step process. In the first step, we have developed a silicon ink. I'm going to tell you about this in the next slide. So we introduce the silicon ink to the substrate, and then wherever we want to metallize, we print the silicon ink, and then we put it into a bath containing metal salts, and then wherever we have the silicon particles, we turn it into a metal. So And the silicon formulation, the ink formulation we have, is actually completely biocompatible, and you can literally drink this ink. It's water-based, and it only consists of some silicon particles and carboxymethyl cellulose, which is a food additive. If you buy some, let's say, bread from the store, grocery store, sometimes you even see that they use such compounds in making bread and so on. So we went from like an ink, which is the commercial one, that consists of all kinds of polymers and solvents and so on, to a very safe ink in a way. And the way it works is that we have the metal particles, and then that are printed on the fibers, and then once we dip it inside the solution, the metal ions get reduced on the silicon semiconductor surface, and then they grow, and eventually they form a coating around the semiconductor material, and as soon as these particles they start touching together, we get a conductive network. And this is kind of what the process looks like, or the products look like. So this is paper after printing silicon ink, and you see the pores are still there. And if we metallize with gold, this is kind of what we get. So the gold process is not that perfect. It's not super uniform, but they are still very conductive, and that's what we want. So here, for example, there's a cotton textile. Again, we print silicon ink on it, and then if we deposit silver, and then you see you get silver process actually works really well, and then we get really uniform, nice looking coating on the fibers. And using our process, because bulk of the material is kind of silicon, so we only have a very thin film of metal, we actually end up using significantly less metal as well. So our process uses approximately 20 to 50 times less metal, and especially for making biosensors, you need a lot of precious metals, and we can reduce that substantially. I would like to check time. Okay. So, and these metals are quite conductive. For example, if you print, we get about 3.5 square. That's on par with the commercial inks, and they're so conductive that it's even possible to make antennas for RFID devices. You know, I'm sure even your college cards might have such antennas in them nowadays that you tap on things to access things. Most of them have such devices inside. And but what we really look or investigate is the development of biosensors using such inks. So we decided to develop a 3D paper analytical device, just purely using printing. And this is a multi-layer device that consists of electrodes. And so we essentially print wax barriers, and then we print our electrodes, so counter electrode, working electrode, and directly underneath we have a reference electrode. So all we need to do is put our sample here, and then it wicks through, and then it forms a 3D and three electrode electrochemical cell for point of care analysis. And then we wanted to use this for the detection of microbes. We were particularly interested in this pathogen. So it's called Mycobacterium avium subspecies paratuberculosis. This doesn't infect plants, but it's an infection agent for animals, and there's also there's some association also with humans as well. So with human diseases, so it causes Yanni's disease in ruminant animals, and this is an interesting disease because it affects large number of animals. Especially dairy cows are under a lot of threat. In Europe, some estimates say that 75% of cows, they already carry this, and it actually reduces yield. Cows produce less milk, and the fertility also goes down, and it's a deadly disease. So once actually cows, they kind of develop them, they need to be culled. So So in humans, it's associated with Crohn's disease. So we try using our devices. We try to detect the DNA of this pathogen. And the way our system works is that whenever you have a hybridization event, so we have these redox active species in the liquid that we introduce in the sample. And then whenever we have a hybridization event that might be a result of PCR, let's say, we capture. So some of these redox active species, they get trapped between the strands. So if we have the target molecule in the solution, essentially our signal just starts going down depending on the concentration of the analyte. So our chips or our electrodes are electrochemically active, and they need to be, because otherwise they won't work. And we could detect low concentrations of the reporter. That's important, because if we can't detect low concentrations of the reporter itself, that means we cannot actually build a sensitive test. So if we do the DNA tests, these are just proof of concept experiments. And then, for example, we have our reporter here. We get a signal. And then we add the captured DNA into our solution. Our signal doesn't change. We add control DNA. Our signal doesn't change. But as soon as we have the target, we have a significant drop in the signal. So actually, this approach seems to work quite well. And right now, we're continuing to work on this project to take it further using a slightly different technology. We would really like to bring this to the farmers eventually. So we have another ongoing project just related to the detection of MAP. And of course, it's also possible to build biosensors that can detect proteins. I'm not going to go too deep in detail due to time. But again, we're able to detect proteins at lower concentrations using such materials down to 50 nanomolars. And these materials can also be used in the detection of, or optical detection of, or optical measurement of pH, because these metallic structures, they can be functionalized with pH-sensitive compounds. In this case, this is an optical device, so we functionalize the surface with 4 MBA. It can be used in surface-enhanced Raman spectroscopy. This peak here is pH sensitive. By essentially optically measuring this peak, we can tell the pH solution without ever touching the sample, that we think may be useful in cell cultures and so on, if we want to measure the pH without ever interacting with the sample using probes and so on. And of course, if we can make electrochemical sensors, it's not too far-fetched to make electrochemical, the other electrochemical devices. Also using this method, we built some we built some batteries, and these are disposable batteries that could be essentially printed onto the point-of-care devices that we produce, and they carry enough energy to power such devices for approximately 10 to 15 seconds, and oftentimes that's really all you need to run a very quick test in the field. As you see with the glucose tests, for diabetics, you only need about 10 seconds or so to get a meaningful result. So moving on, I'm going to have to hurry up. I'm running out of time. So we also work on actually e-textiles for automating electrofluidics. For example, for sample handling is really important for chemical sensing. You often need to mix things and then wash things and so on. And if we want to really reduce error, because most of the error is caused by human handling, really, pipetting errors and so on, we have to automate things. And for this, you need valves. But there are no really disposable valves, and that's what we kind of try to look at. And so we developed a system that can actually that can be electrically activated. So we exploited the phenomenon of electrowetting using e-textiles, and to essentially for valving. And the way it kind of works is that we have a e-textile that contains metals, and on the surface of the metals here, we have a polymer coating. So there is no essentially electrical path between these two. But what we can do is that we can polarize the metal with respect to the solution. We can apply a potential, and then as soon as we do this, actually surface goes from being hydrophobic to hydrophilic, and liquid essentially starts wetting the surface. And then if you have a piece of, let's say, paper at the bottom, as soon as the liquid touches the paper sucks down all the liquid. So we're able to essentially move the liquids around using this method. And I have a video here. So this is kind of the way it works. So we apply a potential between the drop and the metal mesh. And as you see, liquid gets slowly sucked in. And then when we reach a threshold, it gets completely sucked down, and it gets moved to the layer at the bottom. And we can apply many different, like many cycles on these devices. They work relatively well. The only issue with such devices is that they require really high voltages for operation, which is a bit of a problem with disposable devices. However, we have also solved that. I will explain in a second. So yeah, this video is a bit long. I'm gonna skip, I think, the last part. And as you see here, we have a metal needle touching the drop. Well, we don't have to do it like that. We can always just print that needle as well. So for example, this is one device where there is no needle. So we are looking at the bottom of the device. So the textile and the electrodes are at the top. And so we actuated the device using a printed electrode, and the liquid came. And then this one is a mixing device. So we first introduced the first sample, and then now we waited, and then we actuated the second one, and we were able to do timed actuation essentially. Anyways, I'm gonna move on. We did a lot more than this, obviously. We actually ran this is the electronics that we developed for using such devices. And as I said, it requires high voltages, but what we realized is that disposable batteries, disposable cameras that you can buy for a couple of pounds, they actually have high voltage circuitry inside. So we literally took one of these and then we reversed engineered it into a device like this, and then they can produce 600 volts just from a single AA battery. So you can make portable devices using such equipment. And then we also developed an iodate titration assay. This is an automated assay. It's very time sensitive, and again we were able to automate the whole thing using such devices that could mix the sample and then wait till the reaction happens and then apply it to the indicator. But anyways, I'm running out of time. I will just briefly talk about the last thing that we're working on. So we've been working on paper-based printed gas sensors for monitoring food spoilage. So there's a huge problem in the UK and across the globe really with food waste. We produce a lot of food, that's true, but actually most of it end up in the garbage. So even in a small country such as the UK, 4.2 million tons of food gets thrown away that's otherwise completely good to eat. So this costs a lot of money. It costs about 12.5 billion pounds to the economy. And so the way we kind of like keep track of freshness of food is by use of use-by dates. So for example, if you buy a pack of food in a supermarket in the US or in the UK or wherever, it will say, okay, well, you know, it has 5 days. If you don't eat it within 5 days, you kind of can't eat it. You need to throw it away. And even though we actually have these conservative use-by dates, by the way, the use-by date does not necessarily mean that the food has gone bad, because it's kind of conservative. They don't want to take any risks. Although we have these conservative dates, still 1 million people end up in the hospital because of food poisoning every year. So we get sorry, not 1 million. We have 1 million cases of food poisoning. 20,000 people end up in the hospitals. Some 500 people actually end up dying because of food poisoning. And this is also causing a huge problem in terms of the healthcare costs. And on top of it, if we don't consume the foods efficiently, because we use oftentimes plastic packaging to store the food, and what happens to these plastics? They end up in our oceans as well. So this really is a multi-dimensional problem that we need to look at. So we've been trying to develop a technology that allows us to measure how fresh food is non-invasively, non-destructively. So just basically monitoring the gases released from the food and nothing else. And obviously these devices need to be extremely inexpensive because they will end up going to every single food package. And we've been trying to develop electrical devices because then they can be integrated into NFC tags. These are the kind of device, the NFC is the kind of device that, you know, you even nowadays use for payments and so on from your phones. So it's becoming a very available technology. So we would like to make inexpensive devices that could eventually be integrated into NFC tags that are already actually used in food packaging in the Western world especially. And we want it to be very inexpensive, the whole device with the tag, less than approximately 8 cents. So yeah, we have developed printed paper-based gas sensors. They cost less than one cent. So very, very inexpensive. And if you want to make a very inexpensive device, you need to think differently. You really need to exploit the intrinsic properties of the material that you're using. Because the way we kind of do is that we're like, people have been using paper or plastics, but what they do is that they use these substrates as just carriers. They use this as a carrier, and then they introduce functional materials onto the carrier. But if you want to make a very inexpensive device, you need to use the properties of the material itself. So yeah, we wanted to essentially develop a device that can detect gases, and through that can detect spoilage. And of course, such devices would also be useful in other applications. And one of the things that I have realized while I was thinking about this problem, I have come across such a graph in a fundamental book on paper making, and it just shows that actually paper contains substantial amount of water, even at such relative humidities as low as 30 or 40% or 50%. So at 50% relative humidity, paper contains approximately 5% water by weight. So that's a lot of water. So that means that with a substrate that seems and feels dry, you can do wet chemistry without ever adding water to the substrate. So, and so the conclusion of this plot was to me that paper is always wet. So, and people actually didn't really exploit this thing at all. So, and it turns out that we can probe the conductivity, so we can probe the ionic kind of composition of this layer of water through electrical measurements. For example, if you're measuring the electrical resistance of such a device, and if there's a water-soluble gas around, it comes and dissolves in this layer of water, and it increases the ionic conductivity of paper. And electrical conductivity to measurements just allows us to detect what's going on really in terms of the composition or in terms of the gases around our sensor just by measuring the electrical conductivity of the substrate. So, and that's just the paper really. And the sensitivity seems to be correlated to Henry's law constant, and which is just a constant that it's a proportionality factor that relates the amount of gas around in the vicinity of the substrate to the amount that's dissolved in the liquid. And for these devices, all you need is 2 printed carbon electrodes and nothing else. Very, very inexpensive, very simple devices. It turns out such devices, our devices are as sensitive as commercially available sensors that cost, almost $80. And then we make something that costs, less than 1 cent. And we were amazed by such a technology and such results, to be honest. It was a big surprise to us as well. And selectivity is a bit of an issue for such a device. Although it's very, very sensitive, for example, for ammonia, it's also sensitive to trimethylamine and carbon dioxide that are known to be water soluble. But the thing is that they are sensitive, they are not so sensitive. So for example, for carbon dioxide, it's a couple of percentage concentrate or a couple of percent concentration. For trimethylamine, it's also significantly higher than ammonia. It's because, again, it's related to Henry's law constant. So that's one thing interesting about these devices that's completely different than everything else out there. They need water so they need relative humidity to function. Other technologies that are available right now, they don't function really well when there's high relative humidity. So we kind of fill in a very interesting niche where this technology works really well first and inexpensive, and it works well at high relative humidity. So anyways, we use such devices for monitoring spoilage, as I mentioned, and then we have been looking at I know we're in a vegetarian country, but in the Western world, people consume a lot of meat, and and unfortunately, a lot of it gets thrown away. That's a very sad thing. So it's a high value product, so it's very costly. So we have focused on monitoring spoilage of cod and chicken. So, and these are our results. So for example, when we have, let's start with the control. This is chicken. If we have control, just water, we see that the signal kind of stays the same over time. So there is no increase. But as chicken decomposes due to microbial contamination, our signal increases and increases over time. And these bands are essentially results of microbiological assessment, because at the same time, we're also measuring the level of contamination with microbes. And as you see for this product, actually it took almost like 50-something hours to go bad at room temperature. It's actually quite a long time, so it's still okay to consume chicken even after 50 hours at room temperature. Of course, assuming that it was completely fresh to begin with. These products were, but it may not be the case all the time. For fish, it's not the same. After approximately 4 to 6 hours at room temperature, it's already gone bad, unfortunately. So it requires very careful management of the cold chain. And these are the microbiology results that we ran at the same time. You all know this, like the colony-forming units per gram and so on. And looking at so about 10 to the 8 to 10 to the 9 is basically in the literature where they say, food products should no longer be consumed if the contamination level reaches these ranges. And so these sensors, they produce the same, their sensitivity does not depend on temperature, which was surprising to us. And that means that once you calibrate it at room temperature, you can also use it in the fridge. And that's exactly what we did. And in the fridge, it takes about 4 to roughly, let's say, 5.5 days for the product to reach the levels of contamination that essentially prevents the consumer from eating. For these carefully planned and executed experiments, we actually ended up with the use-by date, which was kind of interesting, which is approximately 5 days or so. But most of the time, it's not very carefully. When you're buying food, it's not really actually that controlled. So, in any case, this allowed us to measure the spoilage, and we also integrated these into disposable tags. I also have a video, but I'm not going to show that because I'm out of time. So they work. We were able to integrate into tags, and I'm happy to show them. Okay, I'm going to skip the video. Yeah, so these are not the only projects that we work in my lab. We also work on other projects, and we have a collaboration actually with Professor Saraf, where we're developing a plant-on-a-chip device that allows us to do real-time monitoring of plants. We try to measure their chemistry as they essentially grow and then get exposed to various microbes. And then also my colleague Max here also talked about the other project yesterday that we developed. We're trying to develop in-field detection strategies for measuring nitrogen and also do predictive analysis. So in the last year we launched 3 companies from the lab to develop these technologies, these ideas into products so that everybody can benefit from them. We launched these companies, but of course that's far from saying that they have been successful. And that's kind of part of the game that we have to play. When you develop deep science, deep tech technologies, the failure rate is high, but all it takes is winning once. So it will already improve lives significantly. And I'd like to thank my sponsors for allowing us to do this kind of research, and my collaborators, and of course my host, Professor that arranged really everything. And I'd like to thank my group, and thank you very much. I think I'm out of time, so I don't know if I will take questions. I don't know. But I'm happy to answer any questions.
Any questions from the audience?
Very informative, very good lecture.
Thank you.
Just one question I want to ask that what is the limit of testing? Like if it is for food spoilage, you have mentioned, that sensor shows that it is very sensitive, but what is the upper range?
Yeah, so the question is what's the upper range of detection for the paper sensors that we develop? Honestly, the range is really, really wide. It's because essentially we're limited by the levels of saturation, saturation in terms of the dissolution of the compounds. So, and for example, ammonia is highly water soluble. So we can dissolve almost like half a kilogram of ammonia in 1 liter of water. So we were able to So we tested in the lab up to multiple percentage of concentration of ammonia, and we still didn't saturate the output. So we don't know the upper limit, in short.
Okay. And whenever you are testing it with a food or any environmental samples, it contains many organic and inorganic acids. So does it give with the same sensitivity under that?
So yeah, again, I will repeat the questions because I don't know if you hear them. So is it also sensitive to other organic acids? So the sensitivity depends on the really the Henry's law constant, which is it tells us how soluble a gas is in water. So as long as the gas that we want to investigate is highly water soluble, we can detect it. For example, hydrochloric acid, which is a gas, is highly water soluble, we get a very good response. But for example, like carbon monoxide, it's not a gas, but carbon monoxide is not water soluble at all. We get no response. So it's all about, it's all related to this Henry's law constant, it appears. Yeah.
And last question.
Yes, please.
As I'm working in the field of environment, what do you do when the end of life of this membranes? Because it contains like few of your sensors, they are containing precious metal like silver. And you said incineration is not an approach to discard that chip.
No, I mean, that's a very valid point. So basically, one way to handle this would be to really recycle the metal itself. So you can burn your sample, but you can keep the ashes. I mean, we have not really, like, we're not recycling experts, so we would need to talk to an expert. But the way usually these tests are done is for point of care diagnostics, the test in the end gets thrown away because it's contaminated.
In that case, I can help you.
Okay.
I have the bacteria which will leach out those precious metals at ambient temperature and pressure. So end of life, that membrane, you can send it to me. I can
extract the metals. That's really, really useful. Thank you very much. Yeah. So may I pack up? Okay, thank you. Oh yeah.
Is it there is an interference of other compounds?
For the gas, you mean?
Yeah, for anything. Interference of any other compounds, will it affect the sensitivity?
Yeah, absolutely. So we don't do much for selectivity. So the gas sensor, for example, it is selective to a whole bunch of things. So the selectivity is selectivity. These sensors, they produce higher response for gases with higher Henry's law constant. So the selectivity comes from intrinsic like the mechanisms of the sensor itself.
The presence of other compounds may interfere.
May interfere. Of course, absolutely, they interfere. For example, if you have ammonia, you have trimethylamine. So if you have ammonia, let's say 10 ppm of ammonia, it will produce, a certain response. If you add a little bit of trimethylamine, it will increase that response, but just a little bit, because most of the signal will still come from ammonia, because it has significantly, the sensor is significantly more sensitive to ammonia. Yeah. Okay, I'm going to pack up now. Okay. Thank you very much.
Thank you, sir, for your knowledgeable talk on different bioengineering devices, which is useful in the food science, agriculture science, medical science, and in textile field. Now, our next speaker is Dr. Ajay Khandelwal. I would like to invite Rakesh Panchal, sir, to welcome him with flowers and memento. Thank you, sir. Dr. Ajay Khandelwal, having approx 25-year experience in working in pharmaceutical quality assurance and quality control function, post-graduation in microbiology from Barkatullah University, Bhopal, doctorate in microbiology from Gurukul Kangri University, Haridwar. Currently, he is working as a director with Procter & Gamble Limited at Ahmedabad. Sir, please.
It's Sure. Good afternoon, everyone. Sorry, in fact, it's good morning, not yet good afternoon. So, it's really my privilege to be present here and delivering my experiences of last 25 years working in pharmaceutical industry. Many of us might be wondering why certain tablets are costing much lesser than the same product in the injectable manufacturing. Is it that something pharmaceutical companies are exploiting the consumers? A very valid question that comes into the mind. And that's why I thought many of you might be planning to enter into pharmaceutical industry, because after microbiology, graduation, post-graduation or higher studies, either research or industry are the options. So let's understand why certain products are at higher value compared to other products, and that is basically I want to draw attention of the team or the audience. And my topic is clean room design, qualification and monitoring. So basic objective of this lecture is to understand what clean room is, what should be the design requirements, how we should design that clean rooms. Once we have designed, industry, it's very important that we qualify everything. Unless and until it is not qualified, it cannot be used for the routine activities. And once we qualify, how to get assurance that it is going to perform same way as it was doing on day one versus a year later or 5 years later or 10 years later. So to be very simplified way, a clean room is an area which with controlled environment with low particulate contamination. So it's a room as the other normal rooms are there, but there is a special rider attached to it that the environment should be controlled and the particulate contamination in the room should also be controlled. It should be much lower than the normal room which it can have. So very first the concept of clean room came in hospitals, where into the operation theaters, into the special wards where the patients were kept separately, especially if we talk about burn wards where majority of your body part is exposed because of the burn injuries. And it's not something which has come down recently, it is a more than 100-year-old practices which is being followed into the hospital and operation theaters, etc. It's very important tool to control particulate and biocontaminations. Mostly used to manufacture high quality products, and it's not only pharmaceutical, it's also used into manufacturing of semiconductors, pharmaceuticals, flat displays, the LCD screens, etc., photonics, and space program. Now, is it clean room itself is part of solution? Yes, it's part of solution, but it's not the only solution. Just designing a clean room doesn't mean that your procedure, your product or your intended activity is safe to be conducted. So you have to not only design an area which can reduce contamination to the process and materials, and it can be accompanied by reducing or removing the contamination sources. That means clean air, stable temperature, stable humidity, clean water, gas, chemicals, lighting, processing equipments, inspection, testing equipment, and room infrastructure, etc. So all these things has to be taken care when you design a clean room or you start manufacturing a pharmaceutical product for the human consumption. So now the initial definition versus the new definition which we would put forward is clean room is now an environment where the particulate contamination and bacterial contamination are limited to a prescribed limit. You cannot eliminate either particulate contamination or bacterial contamination. We talk about lot of our sterility, but achieving sterile areas or achieving sterility into the environment is next to impossible. Only what we can do is we can control to a certain level of limits, which is based on the experiences, based on certain risk balance analysis. It has been established that this is the safe lever to work with. So where this contaminant can come from? It can come from personnel, it can come from your procedures, it can come from your equipments, premises, environment, raw material, packing material, everything. Anything and everything which is there into the environment, there is a probability of contamination that can happen into the your environment. So people, they contribute about 75% of contamination into the clean rooms. Ventilation system, when we talk about ventilation system, is the supply of air and return exhaust of the air. So input and output of air, that contribute around 15%. Room structure, the material of construction, the way room has been constructed, the dimensions, heights, flooring, joint between wall and the ceiling, wall and the floor, all these things can contribute up to 5%. Equipment again contributes around 5%. Contaminants are the product and the substance other than the product manufactured. So anything what you intend to manufacture other than that are known as contaminant. It can be foreign particles, it can be particulate matter, it can be microorganisms, endotoxins, anything which is unwanted for you is a contaminant. And then there is a cross contamination. So just imagine that you are manufacturing product X in this room and product Y in other room. So for this room X becomes your material, but X material going into the next room where Y product is getting manufactured, it becomes a contaminant. Although you are interested in that product, but it a contaminant to Y room because you are manufacturing a different product. Just imagine if you are manufacturing a product which is for pediatric use, so for the kids, maybe a cough syrup or a mild syrup for that cough and fever, etc. And it get contaminated with highly potent product like which is to be used for blood pressure management or your diabetic management. What will be the impact of that small quantity of contamination going into the product which you are manufacturing for a kid? Contamination of that product into this product may not have that severe impact, but it still is a contamination or cross contamination. But definitely a small quantity of your diabetic drug or a vasculocardiac drug going into the pediatric drug will have a very, very severe impact on the kid who is going to take that medicine. So not only contamination, we have to also look after the cross contamination that can happen into the manufacturing of pharmaceutical products. And no organization can afford to have a dedicated facility for every product to be manufactured. We have to share facilities between the products. It cannot be viable for any organization to have a dedicated facility. I am going to manufacture only paracetamol tablet in this area. It's not possible. So there has to be change between the product, between the category of product, not only within the category, between the categories. You may have to manufacture different type of dosage forms into the same facility or adjoining facilities, and therefore proper design of clean room to ensure that it avoids not only contamination but also the cross contamination becomes very important. So cross contamination is contamination of a starting material or a product with another starting material or a product. Your contaminant can come from outside air, through dust, which is coming either through the material movement, man movement, or from the airs which is supplied into that area. It can be generated from the pupil. The general study evaluation says that within 24 hours, more or less, we shed skin, our outer layer of our skin, which is almost equivalent to your surface area. So you can just imagine what is the quantity of particulate matter we are shedding into our day-to-day life. So between 1,000 to 10 million particles per minute, which is less than 0.3 micron. And when we say the smallest particle size which we can see by naked eye is 50 to 60 microns. Our hairs are approximate 100 microns. You can imagine what is the level of particle size we are talking about. Normal walking, we liberate around 5,000 bacteria per minute, and single sneeze can release 1 million bacteria during that process of sneezing. So we were talking about food in the previous lecture get spoiled if the contamination level is around 10 to the power 8 or 10 to the power 9, and just one single sneeze is giving contamination of 10 to the power 6 bacteria. Manufacturing process, your equipment, your facility itself can add to the contamination. Cross contamination, it generally comes from a poorly designed air handling system and the dust extraction system which you are using into your processing areas. Poorly operated and maintained air handling system. Inadequate procedures for personal and equipment management. if you are not having a properly designed procedure for management of your human beings working into the area, your equipment maintenance, that can also be a possible source of contamination into your area, and insufficiently cleaned equipments. So just trying to show that if your contamination which is coming from your environment into the same area is contamination, but if it is from this area, if it is going to the other area, it becomes a cross contamination. So same thing can be contamination as well as a cross contamination. We can avoid or minimize cross contamination by personal procedures, adequate premises design, use of closed production systems, avoid opening of the product direct to exposure to air as much as possible, avoid touching with the hands or any ancillary equipment. Try to develop a system which can automatically transfer your product or material from one step to other, and this is possible. It happens in many potent drug manufacturing facility where the person doesn't touch the product at all during the entire process of manufacturing. Adequate ventilating and cleaning procedures, appropriate level of protection of the product, and correct pressure cascade. When I say pressure cascade, it is very important that just not creating positive pressure or negative pressure into the area. It has to be gradual cascading of the pressure differential between the adjoining area, so that you can ensure that the airflow direction into the area is always in one single direction. Depending on the type of product you manufacture, the type of material you handle, it can be positive pressure cascade wherein your core processing area is highly positive pressurized, versus the adjoining area gradually it is decaying. So let's say, for example, if my pressure is 20 Pascal in this room, the next room can be 15 Pascal or 10 Pascal, and subsequent adjacent room to that can be at 5 Pascal, and the next room can be at 10 BM. So that makes sure that whenever airflow will happen, it will happen always from this area to the outside, and nothing from outside can come inside. But at the same time, there can be situation where you are handling potent products such as hormones, carcinogenic substance, where even the environment or the people can get impacted out of the material particle, dust particle which is flowing out from this area to the outside area. And that time we try to develop either a concept of bubble airlock or a sink airlock. And when I say bubble airlock, that means the airlock is, there is a small room which can be as good as 4 feet by 4 feet or 6 feet by 6 feet, depending on the type of process you want to do, number of people you want to enter and exit from that area. So size can vary, but there is a small room between the two adjacent rooms which is highly pressurized, and that makes sure that the air from that airlock goes into the two adjoining areas. So whatever I am doing into this area will remain into this area only, it will not go into the next area, and at the same time I am taking care that the external environment is not getting contaminated out of the due to pressure flow that is happening into your area. And other is the same type of thing where the room in between can be highly negative, and it sucks air from both the adjoining area, and it is being removed from the area and ventilated outside into the atmosphere. So I have already discussed how contaminant can be removed. So it is by the efficient filtration of air. A good, sufficient quantity of filtered air has to be continuously fed into the room through ventilation system. So there will be similar to your air conditioning system where split AC which you use at home. The outdoor unit is outside, indoor unit just keeps on circulating air at a particular temperature, and so the same way HVAC system, heating, ventilation and air conditioning system does. It's a bigger type of split unit wherein the system is designed outside the building, and there are the ducting and the tubings which feed air into the room, and there is a return supply also, which sucks away the air from the room, and it is being getting, there is a process of filtration, there is a process of maintaining temperature, humidity into that air, so that when it gets recycled back into that room, it is, if not 100% pure, it is at least good enough to ensure that the pupil and the product is not getting impacted out of it. The concept of dilution, when you keep on continuously adding some quantity of fresh air into the air, which is getting recirculated into the environment, and normally it is around 10 to 15% of air recycled. So 85 to 90% of air is recycled. We exhaust 10 to 15% of air depending on the process and the product requirement, and every cycle there is an inflush of the fresh air along with the recycled air. Now that is more on the what are the basis why we need a clean room design, what are the contamination, how does it take place, what are the ways and means to control contamination. But now comes the important aspect, how you design a clean room. What are the requirements which we should consider during designing of a clean room. As dust is a carrier, dust must be controlled. The maximum contamination that happens is because of the dust, so you have to make sure that the outside dust should not come inside the rooms. What is the level of microbial contamination you are expecting into the area, and your system should be designed to control those microbial population by process of filtration. Internal bacterial distribution that can be controlled by directional flow of the air by flushing or dilution. So depending on the size of the room, the design of the room, activity you want to perform, there can be various way of achieving this. Very simple example I can quote it, the laminar airflow which you use in the lab. So you don't need entire room to be very highly controlled environment for doing your experiments, whether it's a culture transfer or any type of other microbial manipulation. You are good enough to have a small workbench which is having a clean environment with reference to bacteria contamination. More you are concentrated with, but there is also non-viable contamination that also is controlled by the laminar airflow when we talk about. And for your experimentation, probably non-viable contamination doesn't play a major important role, because you are looking into the growth of the bacteria, so growth of the microorganism which is of your interest. But just imagine my air is fully contaminated with dead microorganisms, gram-negative microorganisms, which can be a possible reason for your bacterial endotoxin, and thereby by eating a product you may feel that your body temperature is getting increased. So for routine microbiological experimentation, you are least bothered about it. Any dead bacterial cell, if it is getting on your agar media, whichever is agar media or a liquid media, it will not grow, and therefore it will not interfere with your experimentation. But for a drug product, it has a severe and significant impact on the quality of the product. So by designing a laminar airflow, you are ensuring not only viable contamination but non-viable contamination is eliminated from that particular workbench, which is a small 4 by 2 feet or something, small workbench. But similar type of design we construct for entire room into the pharmaceutical industry, where we manufacture all our injectable products. We don't do that similar type of designing for solid oral doses, that is the tablet capsules, but we have to do that product, similar type of this type of designing, class 100 area, which we call into the pharmaceutical, or class 8 area. So this is absolutely necessity for ensuring that the product which is getting injected into your veins or your body is purely free from any type of viable and non-viable contamination. Surface bacteria on the surface of your equipment, on the floor surface, wall surface, is taken care by defining proper cleaning procedures, proper sanitization procedures. Just to have this type of laminar airflow, either it can be a vertical laminar flow or a horizontal laminar airflow. You work into your day-to-day lab experimentation activities. So air supply can be from top or it can be from the sideways, depending on the type of activity you perform. Normally when you intend to handle live organism, it should be always from vertical to down, so that you are safe. And when you intend to have say analysis of your material or where you are not handling live cultures, it can be horizontal flow where any contamination which is coming is getting flushed out outside the working area, and your working area remains very neat and clean. So this is one of the just an example of what clean room looks like. Very clean, nothing. So you can see the walls and the ceiling, the walls and the floor and the walls and the ceiling, there is a probing being done. That means it's not joint at 90-degree angle, it is curved surface. And the reason behind is you don't want to create any area where bacteria or dust particle can settle and develop over a period of time. So you design surfaces which is as smooth as possible to ensure that it is getting cleaned very efficiently. At home also, unless and until you pay special attention for the joints between the floor and the ceiling, or between the wall and wall, the corners you cannot clean by the normal cleaning procedure. You have to once in a week or 15 days, your mother or wife, or sorry, you may not be having wife at present, but that is my wife, she takes care of this. So a special cleaning procedure has to be adopted for cleaning those joints and everything. But in the clean room, we design in such a way that we don't need such a special procedure. We curve it so that it can be cleaned by the normal cleaning procedures. We avoid creating too many joints and crevices into the clean rooms. There should not be too many protruding areas into the clean rooms. The walls and the ceilings and the floors, everything should be flushed very, very efficiently as well as possible. Certain things are beyond control. You cannot control everything, but whatever is possible to control, that has to be done. This another example that is, once you enter into the clean room, you are heavily guarded and you can feel like an astronaut going into the space. So it's not, you are not against the gravity, but you are dressed in such a way that your entire body is covered. Mostly only eyes are open, and for when you do the critical activity, even eyes are protected with the goggles. So we try to eliminate possibility of generation of any particulate contamination. And henceforth, whenever I am talking about particulate contamination, it includes both viable contamination, which is microorganisms, and non-viable contamination, which are the dust and the particles. So these are especially designed clothes which doesn't shed particles. Your normal clothing, it also shed particles. So this clothing structure doesn't shed particles. It is stitched in such a way that no thread or anything can be leached out of it. your entire body covered in such a way that no part of your body is exposed, right from toe to the head. Everything is covered. Only your eyes are open, portion of your eyes. That also when you start working with that actual working on the area, you put goggles on onto that area. So, and these goggles are not the normal goggles which we used to wear for protection against sunlight. It's a specially designed transparent white specs. It should not be called as goggles. It can be called as spectacles, which is covering entire of your open face. So your material construction should be of good quality, should not shed particles or support microbial growth. So wood you cannot use into the manufacturing areas and the clean rooms, because wood can be the substrate for microbial growth. Mild steel, cast iron, etc. cannot be used because they are having property of getting rusted, and rusted iron material can shed particles and it can increase the particulate contamination in the area. Normally ready to use partitions are preferred than brick wall. We can have brick wall construction, but then it has to be very smooth. The treatment and the coating and everything has to be done. And as an alternative to that, ready to use partitions are available in the market that can be used for construction of your clean rooms. Floor should be monolithic. When I say monolithic, that means that joint should not be visible. It has to be uniform. So normally we do epoxy coating over the floor so that it gives me a uniform continuous layer of layer. I discussed that wall and ceiling and wall and the floor should be coved. That should be coving to the surface. There should not be cracks and crevices into the area. Unwanted edge and rotation are not acceptable. So sometimes we design similar type of beams, etc. into the clean room. These are not acceptable. The way it is there into this room. For this room, it is okay because it's not a clean room. But when we design a clean room, it has to be uniform, properly flush to the wall. Air venting, lighting fixture should be flushed. So nothing should come from the ceilings, from the walls, from the floors, and it should be a single layer type of design. Drain should be avoided in the clean room, but then the question comes how to clean the area. So there is a probability that you may not avoid the drains into the clean room. Then there are special designs of drains which are known as sanitary design of drain system that should be provided into the area so that your drain doesn't become a source of contamination into the area. Area should be painted with antifungal paints so that it doesn't support and help growth of microorganisms. Air handling system should be installed. Filter combination should be used. So granular filters, fine filters and HEPA filters are used in series to ensure that you achieve a proper level of cleanliness into that area. So normally the granular filters are something around 10 micron or 5 micron filters, which is primary filtration activity. Then next to that is maybe a 1 micron or 0.8 micron filters which used for the fine filtration, and then there is a finally HEPA filter which is 0.3 micron filtration. The basic purpose of having a series of filters is to protect your HEPA filter, which is very, very costly thing, and it cannot be cleaned or repaired, or it has to be replaced. If it gets choked, if it gets damaged because of the any particular impact onto it, it has to be replaced. Whereas by granular filter or the fine filters can be removed, cleaned and reinstalled into the system. So normally we apply some certain level of pre-filtration into it so that my HEPA filter life becomes, it can be prolongated, and I don't have to keep on changing HEPA filter every now and then. Air change in the room should be maintained as per the area classification. The area classification concept and other details I will coming into the subsequent slides. But to ensure that there is an adequate amount of fresh air, which is required for human being, human comfort also, that should be maintained. And there is a predefined limits for air changes which should be there. So even if we talk about this air room, it should have minimum 6 air changes per hour. And when we say 6 air changes, that means whatever is in the volume of this room, equivalent quantity of air should be removed from this at least 6 times every hour. That should be the minimum expectation. And when we talk about class 100 or class A area, it can go even up to 20 or 25 air changes per hour. Your system should be designed to ensure that you get desired temperature and humidity. Certain products are very sensitive to temperature and humidity, and the type of product you intend to manufacture, as per that your system should be designed. It should not happen that you want to handle a very humidity sensitive material which requires humidity less than 40% or 20% or 25%, and your system cannot give you humidity level less than 60%. So normal split AC, it maintains humidity between 60 and 70% on an average. But certain pharmaceutical products are there which requires humidity as low as 20% or 25% also. So when you design your HVAC system, your clean room designing, when you have to keep those parameters also into mind, that what are the intended products you intend to manufacture into the area, and what will be the temperature and humidity requirement of those products. Number of supply and return grills should be appropriate to room size. So there are supply grills into the area, and there are also return to that. So supply grills supplies the air into the room, and then return grills that pull the air out of the room, and thereby the circulation of air keeps on being maintained. So those numbers should be appropriate to the size of the room. It should not happen that you have a such big room and then there is only one inlet and one outlet, and that inlet and outlet, it is possible to maintain with that, but then you need a very high size, bigger size of duct and HVAC system to cater that need. So you have, but it is distributed rooms, and it should not happen that your supply and return is just adjoining to each other. Otherwise, there will be a short circuit and the air will not actually come into the entire area. It will just get resucked from the return. So, supply and return should be separated out. Airflow should be unidirectional. There should not be, the pressure differential between the areas and rooms should be maintained. Now, cleanliness of your area or, keeps on increasing on the type of product you want to manufacture. Yes, or we can say therapeutic risk involved into manufacturing of your product. So if you are manufacturing tablet and capsule, the requirement can be, okay, so say something around class D we talk about. When we say no, we want to manufacture some product which are for the parental use or your ophthalmic product which are supposed to be sterile in nature, then you need class C for the preparation activity, where you do all the preparation activities, your cleaning of equipment, your setting up the system, and class A and B. So A is the actual working area where you work, and the adjoining area to that class A zone, into that with your class B. So overall, your design of your area can get impacted because of the various factors, such as number of particles into the area, microbial population into that area, what is the number of air changes you are expecting for that area, air velocity and airflow pattern, filter types and their position. Now filters are also positioned in a different way, as I was discussing earlier, that we have pre-filters, fine filters and HEPA filters. So there can be two concepts of placing HEPA filters. One can be immediately where air enters into the room. On each and every inlet duct or grills we put the HEPA filter, which is known as terminal HEPA, or we have a bigger HEPA filter into the air conditioning unit itself, and that supplies air to the entire room, and there is no need of having HEPA filters in the individual grills. So, and designing of your system get impacted out of it. If I am having a HEPA filter into the plenum, which is into my air conditioning system itself, that means entire downstream ducting and piping system, tubing system should be equivalent to my clean room design requirement. That means I cannot use mild steel or cast iron or something, those type of material into that. It should be absolutely free from any leakages, etc. Whereas if I don't want to go into that type of designing, I can have HEPA filters on individual terminals, and that gives me flexibility of having some relatively lower quality of material to be used on the upstream, because I have a fine HEPA filters at the terminal level. Air pressure and differential between the two rooms, temperature and humidity. So, different regulations, there are many regulations which controls pharmaceutical manufacturing processes. Every country, every region are having their own guidelines to control the pharmaceutical manufacturing. And when we say WHO, which is World Health Organization, or European Community, PICS, which is the pharmaceutical association of particular zone of countries which are falling into Southeast Asia and Australia and New Zealand, those countries. So they are classifying clean rooms into A, B, C and D type of classification. US FDA says critical and controlled areas. They don't, US FDA they don't say A, B, C, D or C. ISPA, which is the International Society for Pharmaceutical Engineering, they say label 1, 2 or 3, and ISO say 5, 6, 7 and 8. So class 5 is equivalent to class A, and class 8 is equivalent to class D, if it want to have a correlation between the ISO classification and WHO classification. And either A, B, C, D classification or class 5, 6, 7, 8 are classification. These are the most commonly followed classification worldwide. This is just to give a fair idea about the level of contamination which is expected during the designing of your room. And if you say that my area is, let's say, classified for class 5, normally in pharmaceutical we look after 0.5 micron particles, which is 3520 particles in the operation condition, and 5 micron, which is 29 particles. But when we go for other manufacturing such as semiconductors and especially with certain designing for aerospace activities, they are even concerned with 0.1 micron, 0.2 micron particles also. Pharmaceutical, we don't talk about anything about ISO 1, 2, 3 and 4, because those are absolutely overdoing for pharmaceutical applications. But semiconductors and space industry, even they talk about class 1 type of configuration. And at least I can imagine what is the level of cleanliness they are expecting. If we face so much problem or so much issues with managing class 100 area into our manufacturing setup, what will be the situation when we talk about an area which is ISO class 1? Just to give you a fair idea about the filter efficiencies. So, if you remember, I was talking about the granular filter, fine filters and the HEPA filters. So, G1 to G4 is the granular filters, which is my primary or the first level of filtration. it gives me filter efficiency something around from 20% to 50%. So 20% of my total particulate contamination gets filtered here, 20 to 50%. Then there is a difference of opinion or classification between different regulations and guidelines. Some say 5, 6, 7, 8 is the fine filters, 5 to 10 is the fine filters. Some say no, 5 and 6 is the intermediate filters, and there are then 7, 8, 9, 10 is the fine filters. But with the fine filters, we expect getting filter efficiency ranging from 50% to almost 95, more than 95%. Then comes HEPA filter, which are H11, 12, 13, and 14. So in this pharmaceutical industry, normally we use H13 and H14 filters, which is sure. So these filters are normally used, which gives me efficiency of 99.97% and 99.995% filter. So when we say 99.97%, so every 100 particles if you have on the upper stream of the filter, 99.97 filter particles will be filtered out by the filter, and still 0.03% particles can pass through the filter media, and it can go into the area. So we talk about garbage in is garbage out. If you are not designing your system properly, you will not be able to maintain area inside the room. So you have to make sure that every step of your activity, you are eliminating the possibility of contamination into the area. Again, air changes. When we say ISO class 8, air change is 5 to 48, and it can go up to ISO 5, which is 240 to 480 also. But normally, we don't go to that high level. We only work with, for pharmaceutical classification point of view, we work with class A can be as good as 40 to 50 air changes per hour. This is the typical schematic diagram for HVAC system. So there is an inlet of air which comes from the atmosphere. It goes through the process of conditioning, which can be heating, cooling to maintain the temperature and humidity. Filtration goes into the room, and then from there it can be, certain portion can be exhausted out and certain portion can be recycled back into the area. Now, once you have designed your area, you need to qualify your system. You have to make sure that whatever design you have done, it is being getting, it is fulfilling your requirement. So normally we do URS, which we say about user's requirement. We define our requirement, what is expected out of the system. Then we do design qualification. So vendor develops this HVAC system, it sends you all the data, you evaluate versus your URS, whether theoretically it meets to your requirement. Then comes the installation qualification. You install the HVAC system, you connect all the utilities, you connect and you ensure that it is being getting installed at the right place with light connections, utilities, everything. Then the operation, you operate, see that it is getting operated. If there is a start switch, you are able to start with it. Emergency stop, you are able to stop it. If there are certain interlocks are there, if you are opening the door, system to stop automatically because it had a safety hazard. They are high speed moving component inside, and it can have a risk to that safety of the person working in that. So all those things we verify during the operation qualification, and then comes the finally the performance qualification, where you operate it over a period of time, collect the data, and then you say, okay, yes, it is not only one time, one day, 1 week, it is continuously able to give me the right parameter, what is expected out of it. I will be skipping some slide because of the time constraint, but gradually, broadly I have already discussed. So during installation, we check the operation of the system, and then the performance, temperature, humidity, air changes, pressure differential, if HEPA filters are there, so there should not be leakage across the HEPA filters. Airflow pattern, it should not be creating any air pocket into the area. And if there is an air pocket, that means that particular zone or that portion of that room is always having a bad quality of air into it, and it can lead into the contamination to your products. So monitoring is a procedure that we do on periodic interval. It can be on every shift basis, it can be on every daily basis, weekly basis or monthly basis. We do certain testing, certain data collection, evaluation activity to ensure that whatever design was done, whatever installation and intended output was expected out of the system, we are getting those things. So we maintain the temperature and humidity into the area. So we ensure that it is being maintained within the specified temperature. Pressure differential across the rooms have been maintained within a specified limit. Proper grounding and aseptic procedures are followed by the person working into the area. So we do viable and non-viable count monitoring on regular basis. When it comes to Class A or ISO 5, expectation is it should be a continuous monitoring throughout the process of your manufacturing activity or packing activity, whatever you're doing. There should be continuous monitoring of the air quality into that area, and the expectation is there should be less than 1 CFU per meter cube of air. ISO 6 or Class B, which is the surrounding area to that thing, it should have less than 3 CFU. ISO 7 less than 5 CFU. ISO 8 if it is for parental manufacturing or injectable manufacturing, once in a day should be done, and it should be less than 10 CFU. And if it is for solid roller, it can be even monitored once in a month, and 100 CFU can be the acceptance criteria for this. Personnel working into the area, surface monitoring, again there are certain specifications defined for every activities, and we follow those monitoring pattern. Viable count for ISO 5, it should be a continuous monitoring. 3520 count for 0.5 microns and 29 for 5 microns. And air monitoring we do in a 2 different way. One is the at rest, which is at the time of qualification, and then at the time of your routine activities, which is in operation. So in operation, except for Class 5, just a couple of slides. Class 5, each area becomes next to this. So when we say Class B, it becomes Class C. Class C becomes Class D because of the operation activity that is happening. Temperature, humidity and pressure differential 2 to 3 times every shift. That is the expectation. And when we talk about shift, it's the 8 hours of working into the do certain parameter monitoring for continuous compliance. So particle count, air pressure differential, air volume, air velocity, and minimum time or maximum time interval between the two readings should be not more than 6 to 12 months for particle count, 12 months for air pressure, air volume, air velocity. Filter leak, contamination, leakage, recovery, airflow visualization, duct leak test, etc. are being followed. And duct leak test is done at the time of installation and at periodic interval, which can range from 3 to 5 years depending on the your type of product which you manufacture. Any questions? Sure.
Because we are running short of time.
No issue, no issue. So, thank you very much.
Now there is 10-minute tea break. After 10 minutes we will meet here.
like to call upon Professor G. Naresh Kumar Sir, Department of Biochemistry, Faculty of Sciences, MS University, Baroda, for his talk. I would like to call upon Dr. Rakesh Panchal Sir to welcome him with a bouquet of flowers and the memento. Sir, please. Professor G. Naresh Kumar Sir has done his PhD in Molecular Biology 1987 from Tata Institute of Fundamental Research, Mumbai. He is a scientific officer at Molecular Biology and Agricultural Division, Kaba Atomic Research Center. He has done his postdoctorate at the Department of Biochemistry and Developmental Biology, Rice University, Houston, Texas. He has supervised around 12 PhD, 2 MPhil and 65 MSc students. Sir, I invite you for your talk on Artificial Microbial Consortia with Design Mutualism to enhance cooperative performance. Sir, please.
At the outset, I thank the organizers for giving me the opportunity to give my talk. I'll be talking on the work what we have been doing on probiotic E. coli. And the human microbe is becoming a super organism. We know we have about 10 to the power of 13 cells, and we realize that in our GI tract, we have 10 times more number of microorganisms, that's 10 to the power of 14. And the number of genes in our body, whatever we have, is something like 23,000 to 30,000 genes, whereas the gene component of the microbial system comes about 3 million. So microbes are what we call the human microbiome. Not only GI tract, we have in the skin and various locations in our body. They are present and they seem to be controlling and determining. Flora is some sort of a resisting the pathogens to enter. They also kill the pathogens by different mechanisms. Some are involved in the nutrient benefits, and some are helping in the immune responses. And then you have some special, even in the presence of so many different bacteria, if you take in the diet specifically certain type of microorganisms, they add further benefit. What we said is naturally itself they are doing benefits, but addition of certain microbes, these are called the probiotics. And large variety of things are called lactic acid bacteria because they ferment lactic acid, and GI tract is either microphilic or completely anaerobic environment. And these probiotics again help in multiple ways. They control the immune system. They also have the antimicrobial function. They help the GI tract motility, reducing the serum cholesterol, eliminating the toxins, and many, many things. So on the top of this, there are something called prebiotics. These prebiotics are the molecules which are present in our diet, which are not digested and absorbed by our body, and they're in it, and they get into the colon. In the colon, whatever resident bacteria they have the ability to degrade them. And because it's an anaerobic environment, they produce fermentation products and they do a lot of benefits. So the prebiotics help the survival of certain type of colonic bacteria, and the colonic bacterial products are going to help us in milk. So that's how the probiotic-prebiotic combination is a very good thing. So they also call this, if a particular organism has both these properties, then this is also called symbiotic. Yeah. Okay. majority of the probiotics, what are known, are what we said as gram-positive bacteria, lactic acid bacteria, and enterobacters considered for many of them are pathogenic, but there are few strains of E. coli which are beneficial. And this has been identified in 1917 and by Alfred Nissel, and the name is given, a strain is named after him, E. coli Nissel 1917. And this has an enormous ability. The gram E. coli infections are very common. About 70 to 90% of UT infections are E. coli mediated. So, when we talk about bacteriocins, these are the proteins made by the bacteria which act against the other organisms. They are almost like antibiotics. They act on the similar type of bacteria, not the other ones. The reason is these are protein molecules. The organisms, whatever is going to act upon, they should have a receptor. Otherwise, they cannot go inside and kill that. Who will have the receptor? The bacteria which are related to that, they have their own function. This is some sort of a broad way. Instead of utilizing their own protein, this protein goes and kills that. So this becomes some sort of a specific, semi-specific way of targeting the pathogens. So, and they have shown that it has very good colonizing ability and many functions. So and all of us know gram-negative and gram-positive bacteria are different. So if you want to take care of the gram-negative pathogens, the E. coli will be much better than the gram-positive one. Interestingly, some of the gram-positive ones also can do that. It seems these are called colicins, which are the act on that. We don't know what is the reason and how it happened. The horizontal transmission of the gene seems to be very interesting. These colicins have gone from the gram-negative to even gram-positive one. That is why some of the lactic acid bacteria also are able to act on that. And apart from all that, we also know iron is very, very important. This you have siderophores, which complex with the iron and take it up. Again, there is specific mechanism. If you have a good bacteria, which has a higher and more affinity-based siderophore, then it will sequester the available iron, and that iron will not be available for the pathogens, and it will eliminate that. So this mechanism is also possible in the E. coli. So interestingly, what people have shown is E. coli naturally also, it is present in the entire GI tract, and this is the first one to colonize the intestine, and it is a natural delivery process. That people have shown that the microflora, what the cesarean operation infants and natural delivery people have a different microflora. In developed countries, cesarean operation almost not allowed unless it is a medical emergency, something required. So that's a very, very important, because people believe natural microflora colonization is very, very important for infant growth and all the things. And using the E. coli probiotics is in situ delivery. See, E. coli, now we know a lot of genetic manipulations. Whatever we want, we can make it the organism to produce this. One of the interesting aspect of any drug delivery, anything, is that how long the drug molecule is present in the blood as a therapeutic threshold. That's what they call like pharmacokinetics and everything. So you have some sort of a formulations when you make nano formulations, everything. You have sustained release of the thing. If you use some sort of a probiotic mediated one, you don't need to bother about that, because once they colonize, they are there for 24 hours or whatever time span. Where I'm going to show you how long they can colonize and stay in the body also. So this seemed to be very, very interesting one. And recently what has turned out is bacteria seem to produce some sort of a vesicles, extracellular vesicles, bacterial vesicles, both gram-negative and gram-positive. These things can carry variety of molecules, small molecules, proteins, RNA, even some pieces of DNA, and interestingly, hydrophobic molecules. They can, because they will be present in the vesicles, in the membrane, lipid membrane, and that will go. So these are turned out to be very, very interesting components. So this is the new things which has come out in last maybe 10 years or so. They're becoming very interesting about delivery. So now we are trying to use this probiotic for health, and from the human health point of view, we are realizing one complicated situation we have called the metabolic syndrome. What is metabolic syndrome? It is a status of a combined parameters. One is obesity, visceral obesity, then some sort of insulin resistance, hypertension, hyperglycemic, low cholesterol. These symptoms which are there, that's, you don't have any disease, but this is called a metabolic syndrome. It's susceptible for any, and this is characterized on the basis of various parameters. How much should be the lipid content if it grows beyond 150 milligram per ml, and decrease in good cholesterol. These are all seem to be, and blood pressure seem being a little bit on the higher side. These are the parameters which are the characteristics, the defined way we can say it is a metabolic syndrome. What happens to this? What is the causes for that? This is, one is genetics, then is nutritional deficiency. This is very, very important. In Indian context, even the latest reports say something like 40 to 50% of the problems, health problems are related to nutritional misbalance. So that's, and of course metabolic defects, lifestyle factors, that's all of us know, I'll not go into the details, and there are certain environmental factors. All of them contribute towards this, and in the case of nutrition point of view, high fat and low fiber diets, this is a very, at least in our country, it's not too much of a problem. We have a lot of fiber in the vegetables what we eat, but in the Western population, they have both the problems, high fat as well as low fiber. And that is say, responsible for metabolic syndrome. What is the effect of this metabolic syndrome? You can see that there is the inflammatory diseases, all kinds of diseases are, this becomes a precursor for that. You're predisposed to large variety of diseases. Then why it happens? Why the disease becomes more pronounced? What we are coming to know recently is something called cellular inflammation and oxidative stress. These seem to, we are now understanding that till now inflammation, we thought there is some problem when we have some sort of injury or some sort of a pathogen enters your body with that. Now that is there, but in addition to that, we're talking about cellular inflammation. That's almost each and every part of the cell, because of some sort of a metabolic problems, you generate the inflammation. And the oxidative damage is also connected with some sort of metabolism. All of us know when we do the electron transport through the mitochondria, there is some stages of the thing, they produce reactive oxygen species. And if there are the metabolic regulation, some way it is altered, mitochondrial functions are affected, then you generate more and more ROS. And we are having a nice correlation with the mitochondrial functions getting affected causes the inflammation. That is one. And reverse. The we'll not go into the details of this, but basically what I wanted to show you is that the diet where you have a lot of fatty acids, free fatty acids are present in that. That causes the oxidative stress, which is coupled to the inflammation. What are the approaches now? There are specific ways we can do. If we try to somehow regulate this oxidative damage and inflammation, then it's going to be better. And interestingly, what we know, antioxidants also have anti-inflammatory functions. So if we have a combination of both antioxidant and anti-inflammatory thing, that is good. And from that point of view, the healthy component, what we have, curcumin, is an anti-inflammatory compound. Only problem with the curcumin is lipid soluble. So from healthy, we don't get enough amount of that. So now you have different formulations. We have nano formulations where curcumin is available. That is very, very good from antioxidant. So the possible, along with that, if you can use some sort of a antioxidant along with the probiotics, we said already they have beneficial functions. If you couple them, probably it is a better strategy. And these are a large variety of natural antioxidant molecules are known from different plant products. All of them are supposed to be better than vitamin C, which is a basal oil. And these antioxidants are characterized in terms of their redox reaction potential. How many times the oxygen species can be neutralized, that is called redox cycle. The ascorbate can take about 4 cycles. That means after 4 times it gets inactivated. So many of the antioxidants, what you're seeing, up to 800 redox cycles. There is one molecule which is called a pyroquinoline quinone. This has 20,000 redox cycles. That means it is about 50 times more efficient than the best antioxidant naturally what is known of, and 5,000 times more potent than vitamin C. Apart from that, it is also known that it helps in the mitochondrial biogenesis. So it has a double effects, antioxidant effects. Antioxidant, automatically it has some amount of anti-inflammation, and it can also increase the mitochondrial function. So energy, metabolism, everything helps quite a bit. So what we have been trying to do is, we thought we use E. coli probiotic, because we know a lot of genetic engineering, everything strategies are well characterized. So we use this as a tool to provide the antioxidant. First thing what we did was, whatever we said, something like 1,000 to 15,000 different bacterial species are there in our GI tract. When you're adding something, you should this has to compete with the natural ones. So if you give some additional property and way of strengthening that, probably it can colonize for a long time. Naturally, what is known here, if you see here, the E. coli can, if you give a dose of E. coli, to monitor how you know from the other thing, you have to label that. We used a GFP label, and then saw that about till 40 days, natural E. coli, initially whatever given, it is there in the rat thing, and afterwards it is not. That means till 40 days, the natural E. coli initially stays there. Then we added one Vitrocilla hemoglobin molecule. Like in our body, what we have hemoglobin absorbing the oxygen, providing to the tissues. These bacteria, Vitrocilla, has this hemoglobin which binds very strongly to the low amounts of oxygen and transfer to the electron transport chain. So microoxic conditions, the bacteria which has this hemoglobin, it can survive and produce electron transport better. So we postulated that if we put it into the E. coli, then it will increase the colonization. You can see that we stopped the experiment after 80 days, it still was very high. And what we also showed is, not only it is being there, here you can see the counts of the GFP thing, and we also tested its antimicrobial property. So whatever you recover from the fecal matter, even after 80 days, it is the same one, and it is showing the properties of what it is supposed to be. Then we wanted to make this E. coli to produce PQQ molecule. There are many number of genes are associated with the synthesis of this. The synthesis itself is very interesting because variety of bacteria which are producing these things have different sets of genes, and there are some which are conserved amongst them. Some genes are conserved, some are additional ones. So really we do not understand why all these genes are there. What is why there is so much diversity, and what happens? But doesn't matter. So what we did is we took one cluster of this and then incorporated into E. coli. So we have done large number of studies, and when you have put on this E. coli, along with this PQQ, we put many other genes. We did large number of metabolic engineering studies where we helped that dimethyl hydrazine, which is a carcinogen type of thing. We showed that this E. coli having the PQQ molecule produced protects against that. Then we also studied on sucrose mediated diabetes, where sucrose and fructose, they cause type 2 diabetes because the metabolism is different. So we have incorporated an enzyme called inulosucrase. So it converts in situ sucrose into inulosucrose and inulin, and so it becomes a prebiotic. Inulin is a prebiotic. So the bad sugar, sucrose and fructose, are getting converted into prebiotics. So in other words, the probiotic has become a symbiotic. So that's what we have done. We showed that it also helps in the ethanol toxicity, basically the chronic alcohol thing, it helps. And because it's a very good antioxidant, it delays aging and the mitochondrial functions are good. Then we also did with the fructose, converting into 2-keto-fructose, 2,5-diketofructose, which is again a prebiotic, and mannitol, using mannitol dehydrogenase. So fructose and sucrose, both we have converted into prebiotic molecules. And then we also showed that because a lot of heavy metals help cause the toxicity by ROS, and so the organism is able to protect against this damage. So a large number of genes have been put into this for oxidative stress, alcohol liver disease, age-associated phenomena, and diet-induced obesity. What we do is generally we use the simple standard vectors, and we use LAC or TAC promoters, which are constitutive, not inducible, so that standard is the high-level expression takes place. What happens is what is happening, both sucrose and fructose in the diet, they get converted into prebiotic. Prebiotic goes into the colon, and in the colon they are fermented, and you produce something called short chain fatty acids. And these short chain fatty acids and preventing the ROS are the whatever beneficial effects are coming is because of this phenomena. Which also, because ROS is not damaging the epithelial barrier, then it prevents whatever toxic effects of the things. So what we thought is now, in the ROS, there are the ascorbate molecule and whatever antioxidant it is, this is a water-soluble antioxidant. In our body, we also require the vitamin E, which is tocopherol, and this is again an antioxidant, but it takes care of the lipid peroxidation. Membranes get damaged again, like the whatever molecules are water-soluble proteins and DNA, nucleic acid getting damaged. Similarly, our membranes get damaged. For that, we need the tocopherol. So what we thought is, if we add along with this E. coli, which is producing PQQ, in the tocopherol, what happens. But now there is a slightly different forms of isomers are there of the tocopherol called tocotriene. So now we wanted to understand the metabolic syndrome problem. To address that, we said that high fat diet causes the problem. This is what is the basis for that? You have free fatty acids are accumulated in the serum, present large amount, and they go inside and cause the oxidative damage. Okay, this is the mechanism for the and here the oxidative damage happens in the as is shown here. Vitamin E is important in the membranes. All there you have whatever antioxidant enzymes and molecules are present, they are taking care of the aqueous compartment. And this tocotrienol, normal vitamin is tocopherol. Tocotrienol is a much better antioxidant in the lipid membrane because it is slightly shorter, so they can get into the membranes much more easily. And people have shown that tocotrienol gives many benefits to the body. So all types of tissues it goes there from the whatever you give, and then protects that. So what we postulated was whatever oxidative damage is there, it is happening in the both hydrophilic and hydrophobic environments. And if you have E. coli Nestle producing PQQ, it will take care of the hydrophobic one. If you have tocotrienol, it will take care of the membrane component. So, and then because ROS is taken care entirely, it will be better thing. What we did was we kept the rats with the high fat diet, and then we gave the control. First one is a control diet. Then with a high fat diet, you can see the body weight increase very high, and then you have PQQ alone, tocotrienol alone, then PQQ and tocotrienol alone as giving just the dosage, and you can see that with compared to the E. coli producing PQQ along with that tocotrienol given. In all these things, you can see that body weight, which is much better controlled compared to all things. So this is clearly says the E. coli producing PQQ alone is not able to take care of entire oxidative damage and entire effect. Body weight is the best indicator of the high effects. So that is come, and then you can see that all this is superoxide dismutase, activity is very high, and catalase is also very high, and then you can see that the lipid peroxidation is almost not found. It's as good as the control. So this is the same thing that was in the liver, and we have also monitored in the RBCs. So similar thing. So the E. coli Nestle producing PQQ, when supplemented with tocotrienol, it is able to take care of the fat-induced one. So and this is the trying to show in the sections of the liver what is the effect. This is the control one. You can see the high fat diet, the tissue is damaged, lot of cells are dead, and here you can see that the E. coli Nestle treated one almost near to the control thing. So and this is that we talk about liver. This is the adipose tissue. Adipose tissue, if you look at that high fat diet, what happens is these adipocytes, they increase in size. They increase in size and also increase in number. That's how the obesity is there. And so you can compare the normal diet and high fructose thing, they are big. And when you come back to the E. coli Nestle, it is back to the original thing. So if from all these parameters it seemed to show E. coli Nestle producing PQQ along with the tocotrienol, it is being effective. And the whatever we hypothesized seemed to be working. So now what is the next? So we want to further improve this. How do we improve this? For this, delivery of tocotrienol every time is not easy. As I said, curcumin problem, same problem is there with this because it is not water soluble. You have to give it in some sort of a fat soluble way. So if we can make the E. coli produce tocotrienol, so interestingly, people have clone these genes. Everything we know about the gene cluster in 2008 itself they have done it. So this plasmid PCAS47, it contains the genes required for tocotrienol synthesis. So a second problem is what we said, how does it go to the cells? Tocotrienol, we were wondering, even if you produce it, it will use for itself, but how to release to the your body? Now this come as a boon for us. Outer membrane vesicles, what I told you, the E. coli bacteria produces vesicles, and in these vesicles we can. So what we have done is, we have E. coli PQQ producing one. We have incorporated this plasmid, and that plasmid is now, these vesicles are from our E. coli Nestle having PQQ and tocotrienol synthesis genes, and these vesicles also contain the tocotrienol. So now we are going to, we are using this to animals and comparing earlier whatever I showed you, PQQ with the tocotrienol, externally adding, and this organism, how it is better than that. So we are waiting for that. Okay. Now, one of the interesting developments what is going on for a long time, genetically modified probiotics were not, they were discussing whether to be given to the as a health component or not. Recently, these efforts are becoming good. People have used, you can see that lactobacilli, E. coli, Nestle also, the first thing I showed you, there are reports. They developed the genetically modified Nestle, and they're trying to use as a one. And variety of lactobacilli strains, probiotic strains are being used. And you can see that bacteria, the Nature Biotech is proposing now the probiotics it's using for the genetically modified probiotics for human health. So, hoping that someday our things will also be useful for the society. Okay, this is our probiotic group. Most of the work, whatever work has done, all these people have contributed for the overall background of the thing. And today's, whatever I showed you, the tocotrienol work is the Shubham, he has done the work. So, thank you.
Any questions from the audience?
What is the pH? At which pH this probiotic works?
Oh, they have to work in the body pH. So they okay. All probiotics have to cross the stomach pH. So you have to test that. Two important things: acid tolerance and bile tolerance. These two tests are generally every probiotic have to do that. But they survive in most of the bacteria are good at neutral pH. That's what I said. Stomach, they cross the barrier. Most of the time 2 hours or something like that. The stomach, the bacteria is there. So that test has to be done before you considering something as a probiotic.
So you said that already the intestinal wall is occupied by
Yes,
the
yes.
normal flora of
Yes.
our body. If I want to take probiotics and I want to get it changed,
Yes.
will those flora allow them to get colonized inside, or how to get it done?
Yeah.
Not AECI.
Anything. Normally also we take that. The simple, okay. In natural microflora, there are two types of microflora. Some things are there, colonized, and they cannot be disturbed. There are other ones is very, very dynamic. Almost every day or 2 to 3 days, they keep changing. So that's why when we talk about microfloral composition, diversity, it's a very, very challenging problem because our diet is not constant, we keep changing, so the microflora changes. So, general thing is, if you are taking large amount of number in the bacteria, these dynamic population can be replaced. So that's what we do. Probiotic capsules, what we take, there's something like 10 to the power of 8 or 9 there. So that's very high numbers, so that they can replace. But their life, how much is going to be there, depends on the organism. This ecologically in the rats I showed you that much. In the humans, maybe a week or so. So human experiments are also there doing that. That's very interesting. People are now seriously considering probiotics, even genetically modified one for thing. But in general, probiotic consortia is becoming a very, very important one. In India recently, there is a probiotic project has been initiated, about 100 crores or 150 crore project. Trying to identify the natural microflora in the Indian population, and based on that try to develop a good probiotic consortium. Yes.
That means you have to keep on continuously taking the probiotics to keep their...
Yes, it is almost like you were saying, no, probiotic lassi, yes. Probiotic ice cream. Normally we have in curd, cheese and everything bacteria there. These are the natural probiotics.
But their flora is not always a constant.
Because even if you take curd from different curds, bacteria is different. So that way it is dynamic. No, that's true. Our thing is very dynamic. So this is one misconception, at least non-microbiologists have this. They think that curd means ho gaya. But all curds will not have the same type of bacteria, no? So it is a specific strain is isolated and then considered as a probiotic. That's how you have a lot of probiotic lassi, ice cream, everything in the market. So although you have normal lassi, obviously this is better.
No, these capsules are available.
Yes.
Bifidobacteria and lactobacilli.
Correct. Bifidum is very good. Yeah?
Supposing you want to...
Oh, you can take it daily. There's no problem. Oh, I do take. I'm taking. So, perfectly no.
That will give you a constant...
And I advise people, if you think that I have eaten something which is possible infection, it can only prevent.
Correct.
Once the diarrhea you have, it will not do much. But it is a preventive thing. Okay? So...
many times the antibiotics also
yes.
they are adding the...
Yes. So that anyway they do. Nowadays all the prescriptions along with the antibiotic they also give probiotic. Yes. But as a microbiologist, I'll tell you, all of you, without worrying about it, you can take probiotic and keep varying the probiotic. Don't take the same probiotic because each company they say mera acha hai, mera acha hai. It is obviously we know the diversity is much better. Okay, so keep varying your probiotics. Whatever you want, every week at least you should take. That's the general my advice.
Anyone else?
Thank you.
Our next speaker will be joining us very soon, so please be seated. Department of Microbiology and Biotechnology Center, University of Baroda. I would like to call upon Dr. Rakesh Panchal sir to welcome her with the memento and bouquet of flowers. Sir, please. She has done her PhD in molecular biology in 1991. She is a life member of Association of Microbiologists of India, life member Society of Biological Chemists India, life member Biotechnological Research Society of India. She has been awarded Kamal Roy Bhatt Award for outstanding academic performance and securing distinction marks for the postgraduate degree in microbiology in MS University. She will be going to talk on artificial microbial consortia with design mutualism to enhance cooperative performance.
Sort by date करो ना, सबसे ऊपर आ जाएगा. Date modified.
Microbe consortium.
this one doesn't work? Laser? Laser, it's oh, is it? It's a smart screen. So how do we point it?
You have to do it just
okay, fine. So thank you for the introduction. And at the onset, I would also like to thank the organizers for giving this opportunity. And it's always a pleasure to visit Gujarat University. We have been coming here often and interacting with the faculty members here. So the talk that I have planned for today is Artificial Microbial Consortia with design mutualism to enhance cooperative performance. So this is something, consortia is not a new word. It's been there for a long time, and we like to use a mixture of microbial strains and we call them a consortia. And then we wanted to do a particular task for us, like provide fertilizer to the plants or carry out bioremediation or do some or the other task which we would like individually. Each of these strains have been tested, and then we just make an artificial mixture of it and then put it in the environment. And most of the times what we find is that we are not sure whether it really works or whether all the strains are performing to their best extent. So in the recent times, there have been a lot of new developments in how to manage the consortia, and many of these principles of how to manage the bacterial consortia have come from studying natural ecosystems and studying natural interactions among microbial species. So I would be going into in this talk, first of all, trying to give you again recap of all the types of microbial interactions which happen in nature and how these interactions can be harnessed for production of biotechnological goods or for doing some environmental remediation or some other desirable application of the microbes for our benefit. And in the end, I will just touch upon a little bit about what we do in our lab and how we use some of this information to develop effective consortia in our lab. So I don't know whether it is really visible. Is it too bright? The light off. Can we have this light off? Maybe it will be better seen. So this slide shows you that microorganisms do not exist in isolation and they have ecological interactions. In fact, the actual real interactions of microbes is in the form of a web. But this is a very simplistic 1:1 interaction of a pair between any pair of microbial species. And we can see in the center, when there is no interaction, we say that it is neutral, they are neutral towards each other, which is very rare. It is actually very rare to find organisms which really are neutral towards each other. Most of the time they have some kind of an interaction which may be either positive or negative, and it could be positive to both the partners, and when it is positive to both the partners we call it mutualism, and it is a win-win situation. And when we try to design consortia, we like to make this kind of a win-win situation for all the interacting partners so that they perform the best and deliver the output that we want them to deliver. But there are other interactions we see which happen among microbes. So we have what is called as Amensalism, where one of the partners is negatively affected while the other one is not affected at all. Or there could be Commensalism, where one of the partner is positively affected where the other is not really affected. And we have the negative interactions which are like competition, can lead to a loss of population of both the interacting partners, or the parasitism or predation. That is also a very interesting type of a population dynamics, because the parasite depends on the host. It cannot completely eliminate the host, and so can't the prey eliminate the predator. I mean, the predator cannot eliminate the prey. So these are the interactions, and this is essentially in a nutshell what the diagram showed. And we have these are simple binary modes of interaction among organisms, but in reality they are not necessarily only binary. There can be multiple players in the system, and it can be really a very complicated web that the microbes have in nature. So a consortium, as I told you, is a mixture of two or more microbial groups which somehow live together symbiotically. And microbial consortia have several advantages over single species, and they have such as the efficiency in their performance, the robustness in their performance, and the modularity of their function. You can divide the function up into different members. So the members of the consortium have to communicate with each other. They are not isolated organisms. They have to communicate, and they have to somehow the overall output of the consortium rests on the coordination between the members of the consortium. So the main idea about the consortium is the division of labor. So we see that if a task has to be performed, it need not be a burden on one species, but it can be divided into a number of different species, and this is one of the key importance of microbial consortia, that there is a division of labor. The other aspect of consortia is how to use the resources effectively. So if you have different microbial species, they have a preference for one carbon source, another has a preference for another carbon source, some uses nitrogen from the atmosphere, one uses nitrogen which is already fixed. So we can actually pool in a large number of resources, and they can be collectively used to produce the desired output. So therefore, this is the other important aspect of microbial consortia, that they can be using the resources more efficiently. And as I said, ecology, the natural ecology, ecological interactions among organisms are what are used as a basis for designing the consortia. So I'll just skip this. This shows how you can use different members of the consortia to carry out different steps of a desired output. And many carbon or energy sources can be nicely partitioned among the community members, and as a result you have much more efficiency of resource management. So if you see here a single population, for example, the upper panel A shows how a single organism has to carry out the entire pathway and bear the load of all the reactions that go on in the pathway, but in a consortium you could have different organisms performing different steps of the pathway. So in order to understand microbial consortia and how to make them stable, how to design them artificially and put them together, we always have been just putting them together and putting it in the fermenter or putting it in the soil, but we don't know really whether it works. So now there are interesting aspects about molecular basis of the interactions among microbial consortia. These new aspects have been understood, some of them. So we know that when microbes communicate in a consortia, they can communicate via some messenger molecules, that is through diffusible molecules, or they can communicate through direct cell-to-cell contact, and both kind of phenomena happen in nature. So we do have direct contact, cell-to-cell transfer of DNA, of proteins can take place, and diffusible molecules are small signaling molecules which can be diffused from one cell to the other and can be used up. So for example, here I am giving you a list of contact independent interactions where there is no contact but molecules are secreted. One of the interesting molecules are quorum sensing molecules. So these quorum sensing signal molecules are small chemical molecules. It could be peptides or it could be homoserine lactone. They are secreted by the bacteria and they are diffusing out in the environment. Other bacteria can sense those signals, and on the basis of the threshold value of the signal, they can express certain traits that or genes that are under the control of this quorum sensing. Now there are also a lot of end products of fermentation which a bacterium throws out, and these might be useful things for another bacterium and they can use it effectively. There are also enzymes which a bacteria secretes for its own benefit, because sometimes it has to degrade cellulose and other big molecules which cannot enter into the cell, so it secretes the enzymes outside. And these enzymes will digest the cellulose or the proteins, but the digested material can be actually useful for any other organism which is in the vicinity. An interesting aspect that has come out in the recent past is the sharing of electrons between microorganisms. So there can be direct conduits between an organism, two species of the organism, where the electrons can be transported, and microbial species interact via electron transports also. So now coming to contact-dependent interactions. How do bacteria actually carry out different interactions through direct contact? So we see here that bacteria have surface structures like pili. These pili can be actually the conduits for transferring electrons in a cell-cell interacting manner. Sometimes conductive materials like activated charcoal, magnetite, they act like a bridge, then they transfer electron from one species to the other. Then bacterial type 4 secretion systems are again pili based system to transfer DNA or proteins. Bacterial type 6 secretion systems are like injectable needles. The bacteria makes a needle through which it secretes proteins from one cell to the other. And there are nanotubes, which are tubular structures or tubular extensions that bridge the neighboring cells to mediate cell-cell communication, where DNA can be transferred, protein can be transferred. So these are all very exciting ways in which bacteria actually interact with each other and communicate with each other. So this is the diagrammatic representation of all the possible ways in which bacteria can communicate and interact with each other. We have seen small molecules, signaling molecules, and there we see the direct transfer of DNA through these secretion systems, which really they resemble actually injectable needles, and they really look like that. The structure is exactly like that. So now I'll just give some examples as we are going through this thing. So some of these examples are a little complex, some are very simple to understand. So this is an interaction between bacteria which carry out sulfate reduction, that is desulfo vibrio vulgaris, and methanogens which generate methane. Now, in these bacteria, pure cultures, if you use pure culture of desulfo vibrio, that is the sulfate reducing bacteria, it actually catabolizes organic substrate and uses sulfate as the terminal electron acceptor. So, sulfate is needed for this organism to grow. Whereas Methanococcus, or the methanogen organism, that assimilates carbon dioxide or formate or small molecules like acetic formate, and they consume hydrogen as an electron donor. Now independently, when these two strains are growing separately as pure cultures, one needs sulfate and the other needs hydrogen to grow. But when we put them together, the sulfate reducing bacteria can actually can survive, and we can see here earlier neither of them could grow in the absence of sulfate or hydrogen respectively, and when they are together, no need of sulfate, no need of hydrogen, they provide each other whatever they require, and such interspecies interaction allows them to grow in environments otherwise which would not be conducive to the growth of each of them individually. So this is our lesson from a natural system like this. So this is the diagrammatic representation of the same thing, that we have sulfate reducing bacteria and we have a methanogen, and the kind of exchanges that go on permit them to grow in a situation where otherwise individually they wouldn't have grown. So contact dependent interactions, again I have mentioned that it is possible that two microorganisms are able to exchange electrons directly via direct interspecies electron transfer. This example is Geobacter metallireducens and Methanoseta arundinacea. So now we come to how to harness these consortia for our application purposes. So artificial consortia are created by mixing appropriate strains of pure cultures which we have obtained in the lab and mixing them in such a way that they perform a particular function. Now these strains are not naturally found in the ecosystem together in the same environment, and they have never probably interacted with each other, right? So they may not have that kind of strong interaction and dependence among each other, but we can artificially generate interdependency also. It can be promoted by manipulating the environment, or we can make some genetic mutations which will permit now these strains which were not otherwise habituated to stay together, these strains can be made to stay together. So these are some of the ways in which we can harness the benefits of consortia to drive a function. So this here is an example of a yellow cell and the blue cell. The yellow cell is actually producing our desired end product, and the blue cell just helps to remove some of the inhibitors or toxic compounds which can be removed by the blue cell so that the yellow cell does the task properly. Same is the case there. The yellow cell is producing the product and the blue cell now supplies some cofactors, some growth stimulants, and these can then be used to make more of the product by the yellow cell. So the blue partner, as you can see, removes or enhances the product formation through these two approaches. And this is an example of a two-way interaction such that we have two different outputs. We want the yellow cell to produce some particular molecule which is of our interest, and blue cell to produce yet another molecule, and we want both of them to be cooperatively producing these molecules or outputs. So we have this kind of a loop which is called as the cross-feeding loop, just like we had for the SRB and for the methanogens. So this type of a situation can be manipulated artificially. I'll come to how this can be done. So we have another example of how a particular organism produces an intermediate, and that intermediate is carried forward to make the desired product by another organism. Again, the two should stay together, and we have to work out ways to stay together. So these are real life examples of organisms which behave in this way. So we have butanol production. The producer organism is C. acetobutylicum, which produces butanol. But the other organism, Bacillus cereus, it is actually just involved in scavenging the oxygen and making condition anaerobic, which is beneficial for butanol production. So similarly, we have another example here. These are again real examples where these are used for industrial production of certain molecules. So we have now fatty acid production by Streptomycin silicolor, and the production of fatty acid reduces the pH in the fermenter, which impedes for the production further by S silicolor because it gets inhibited by a lower pH. So we have some organisms which will maintain pH by removal of the organic acid, and the pH can be maintained, and this will again lead to better production. So same is the case here, where now the product is butyric acid, and the bacillus converts sucrose to glucose because tyrobutyricum cannot utilize sucrose. So we have now another an alternative source of carbon can be used towards producing butyric acid, even though the original organism which produces cannot use sucrose. So we have bacillus which degrades the sucrose or hydrolyzes it into glucose and fructose. So we have again, this is another interesting example where Streptomycin silicolor produces the antibiotic actinorhodin, but it cannot produce it in high quantity unless it gets a signal molecule from the Myxococcus xanthus, which is a predator. So this predator, in order to escape the predator, the organism produces more antibiotic, and that signal molecule leads to greater antibiotic production. So you can see that there can be a stimulation for the desired product formation. So when we want to produce this antibiotic, it is useful to put either the strain or the molecule itself. So there are several other examples. I have several examples here, and this is another example of vitamin C fermentation. This is why I would like to point out this example, is that this Bacillus megaterium, when it is co-cultured with the producer organism, the producer organism is this Chaetogulonosygium vulgare, right? So this organism makes vitamin C, and when it is producing all by itself as a pure culture, the yield of vitamin C is not as good as when it is with Bacillus megaterium. When it is grown with Bacillus megaterium, the yields are high. So people wanted to understand, why are these yields high? What exactly is Bacillus doing in this co-culture? And this is an example where the complete systems biology approach was used, in which we have the genomics, the proteomics, and the metabolomics study compiled together, and using all our genomics and the omics approaches, and based on that, it was realized that Bacillus megaterium supplies a lot of nutrients to the K. vulgare. And these nutrients can be, for example, adenine, guanine, all the purines that are needed. It also stimulates the production of the precursor. And in general, it's not just one molecule that it secretes. It's an array of different molecules which are made available for the producer organism. And as a result, the production is boosted. So now coming to this point, that we can apply microbial consortia not only in industrial fermentation. So most of the examples that I gave you are for industrial production of, say, butanol or antibiotic or various other examples. So now coming to environmental applications. So when we do environmental applications of consortia, we use them as biofertilizer or biocontrol agents. We can do it for reclamation of soil, for degradation or bioremediation, and so many other applications. So in this, we are now going to put the consortia back into nature, into the environment. So what can we do to make our designer consortia? How do we go about making it? So one of the things that we can do is divide the tasks into different members. So if we want to promote plant growth, to divide the tasks up, that we have a separate phosphate solubilizing organism, separate nitrogen fixing organism, separate one which produces IAA or other plant growth stimulators, and make them all together, and then make a consortia. Now in this consortia, the most important thing is, how do we control the population density of all of them? Because they might interact competitively with each other, they will compete for the same resources, and eventually some member may outcompete some other member. So now we are in a position where we can probably understand and manipulate this kind of a situation, where we can give population density control among all the consortial members. And we also have to see that they utilize different resources to ensure long-term and sustainable production or sustainable maintenance of them together. So the key here, the key tagline which I would say is, stay together and perform better, right? So they have to somehow be made to stay together, and we have to ensure that because they stay together, they perform better instead of one at a time. So how do you generate interdependency? So one of the interesting ways of generating interdependency of the mixed consortia that we are going to generate is to develop auxotrophic mutations. So when we say auxotrophic mutations, it means they are deficient in the production of some essential growth factor, like an amino acid or some purine pyrimidine base. So we make, for example, the organism on the left is what is called as delta lyse A, that means it is defective in production of lysine for itself, and it's an essential molecule, so it cannot grow without supply of lysine through other external source. And the other mutant is deficient in isoleucine, so therefore it is having a mutation in the ILV gene, so it cannot grow without supply. So we have a reciprocal mutation in this manner, so that one supplies the isoleucine to the other and lysine is supplied, and in this way we can generate interdependency through cross-feeding and auxotrophic mutations. And I have here this diagram, that one on the right side, it shows how it is possible theoretically to generate a 14-member auxotrophic consortium, because we have large number of essential amino acids. We can mutate each of them in different members, and they can become nicely interdependent, and you can see a web of interaction like this. This is how we can generate a 14-member interaction auxotrophic consortium. Theoretically it is possible. And now this is another example here how we can use the environmental facilitated interdependence. Right, so this is, as you can see here, there are two organisms, a lactate metabolizing organism and a nitrogen fixing organism. So lactate metabolizing organism can utilize lactate and produce acetate or formate, and this acetate or formate can be used up by the nitrogen fixing organism, which can fix nitrogen from the atmosphere and supply it in the form of ammonia to the other. But will it do so under all conditions? No. When there is sufficient glucose, we know that glucose is going to inhibit lactose utilization, so lactate utilization. So glucose, if there is in plenty, then both of them can grow separately without any interdependence. And same is the case when you provide fixed nitrogen in the form of ammonia. When ready-made nitrogen source is available, the organism will not fix nitrogen anymore. And therefore, if you want to make this interdependent, you have to ensure that there is no glucose or alternate carbon source available, and it has to use lactate, and there is no fixed nitrogen available, so it has to depend upon the nitrogen fixed by this nitrogen fixing organism. So now you have an interdependence which is generated through environmental modulation, so that they become completely interdependent with each other. Right? So I'll skip this. Now I'll just give a glance at what is happening at the genetic engineering level, and there are a number of different approaches which can be used to engineer synthetically the dependence among each other of the member, and this can be done through very complicated genetic engineering, what we call as gene circuits. Right, so these are all different types of gene circuits. I am just going to give you one example. So, so in this gene circuit, this is the kind of model which can be equivalent to a predator-prey model. So I would like to say here that this red molecule is a killer protein, and the green molecule is an antidote to that killer protein. Right? And what we see here are some molecules being, made by one cell, going across in the other, and then promoting the molecules made by this cell and going out into this other species. Right? So what we see here is that this molecule is different from this molecule. So this molecule stimulates the genes for expression of this killer protein. Right? And also for the secretion of this molecule, which is going to go here and help in the secretion of this antidote. Right? So when this, this is going to balance the two of them are together, are going to act like a prey and a predator, because one of them is going to have the antidote, the other one is going to have the killer molecule, and in this way we can regulate the population dynamics through putting in these gene circuits. Now what are these gene circuits actually? So you can see these gene circuits are made up of genes which are involved in quorum sensing. Right? So these genes are involved in quorum sensing. We see the LuxR and the LuxI. Normally the LuxR and LuxI are working conjunction. But we have the Lux are working with Laci, because Laci is the quorum sensing molecule which is of the other kind, and we have the Luxi working with the Laci. Right? So we have interchanged the natural quorum sensing signal, and the receptor has been interchanged. So signal is made by one cell, receptor is another cell, and here the signal is made by this cell, and its receptor is in the other cell, and they are controlling this killer protein and the antidote for that killer protein. So this is a wonderful circuit, and there are a large number of such circuitry which can be designed, which can mimic one-way interaction, two-way interaction, positive positive, negative negative, negative positive, all kind of interactions can be manipulated using these kind of gene circuits, and we can have a combination of such interactions which can be artificially developed. So this is how the prey and predator system work. This I already explained. Now consortial interactions can also be used to make specific patterns of microorganisms on a on a physical surface. They can be used to make patterns. So for example, I am going to give you an example over here of strains which were labeled with GFP, that is the green fluorescent protein, and the red fluorescent protein. Two members of the interacting community were separately labeled with the green and the the red fluorescence, and they were mixed in different ratios, and confocal microscopy was done to see how they grew on an agar surface. And what we see is all these different spatial patterns at different ratios. So when there is neutralism, what kind of a pattern we get? What kind of a pattern we get when there is a positive negative negative zero interaction? What kind of an interaction we get when it is the other way around? So what we see is originally the organisms were mixed in a particular ratio, and what happens to that ratio over a period of time, and we can see the green and red spatial patterns that are made, and there can be intricate spatial patterns which can be developed through these kind of interacting this thing. So this is a spatial pattern of a competitive consortium, where you see at the end only one member survives, either this or that. Either you have the green. This is a cooperative consortium, and every ratio of different interacting partners, both of them survive. And this is of a neutral consortium where they have no effect on each other, right? So there are a lot of tools and approaches which can be used to engineer synthetic microbial consortia, and I will just read out this column for you because it's very important to see. So we can see that this application can be degradation, it can be bioproduction, it can be functionalized biomaterials. Biomaterials can be generated, distributed logic computing, which I am not very sure, but biosensing is also an application. So these are the different applications in which these consortia can be used to engineer. Now, what are my research interests? I will just briefly tell you, because how much time is there?
By 1:30 it was supposed to be over.
Oh, I am running out of time. So I will just tell you, we are developing consortia for agricultural purposes, and we look at consortia through siderophore mediated interactions. So siderophores are ion chelating compounds made by microbes, also by higher organisms, and these compounds come in different chemistries. So we have catecholate type or hydroxamate type, carboxylate type. Down below are examples of two siderophores, like the pyoverdines made by Pseudomonas and the enterobactin made by Enterobacteria and E. coli and other such organisms. So these siderophores can mediate such complex interactions among different organisms. Here the example shown is between the host cell, right? So the host cell stores iron bound to lactoferrin. This iron can be stripped off by the bacterial siderophore because the siderophore has a higher affinity. The host also counters that by making a protein which interacts with the siderophore of the bacteria, and it's the iron is captured again. And now this bacteria evolves to make a new type of a siderophore which is going to capture this one even better than the green arrow. And now we can see this kind of interactions which are there. There is all kind of interactions that can take place. And now we are looking at interactions among bacteria. And yeah. So we do these kind of experiments to see. We take one bacteria and it's hydrophore and put it in the well here. And another bacterium is.
Just take a microphone here.
Oh, is it?
Yeah.
Okay.
Try this one. Keep it close to it.
Yeah. So we extract hydrophores from different members whom we want to put together, and we put those hydrophores in these wells here, and there is an organism which is plated on this plate. Now, if the organism can sequester iron from this hydrophore, it will be able to grow around this well, and we can see here growth around these wells which are there, which indicates that this organism which we have plated on this plate is able to use or steal the hydrophores of this other organism, this other organism, and this other organism, and we are trying to see based on this hydrophore interactions how we can develop a PGPR or a consortium of plant growth promoting organisms which will stay together because of their interactions mediated through hydrophores. So that is what my laboratory is working as far as this aspect is concerned. This is just one aspect that we are working on. I just wanted to give just a small idea about what we are doing. So this is the numerical values of all this, and we have concluded which organisms can cross-utilize the hydrophores of which other organisms. So summarizing my talk, I would like to say that I have given you an idea about how the principles of complex interactions among microbes in natural ecosystems can be harnessed to make artificial consortia for a desired output, and this social interaction programming can be used to build a population stability of multiple strains, and it can be generated through either cross feeding or different other whatever I gave you examples. And this social interaction engineering, as we call it, through the combination of microbes, they can create an artificial community with predictable behavior. So our main aim is to make them show some predictable property, and that is what we have to use these systems for that purpose. Thank you. Any questions from the audience?
How bacteria prioritize the one output instead the another in a consortium?
Sorry?
How the bacteria prioritize the one autoinducer over another in a consortium?
One what?
Just a second. How bacteria prioritize the one autoinducer over another autoinducer in a consortium?
So autoinducer are the quorum sensing molecules, and bacteria produce their own quorum sensing molecule so that they can sense their own population around. But there are other bacteria which can have receptors for these quorum sensing, and they can is that what you are trying to ask, how they interact? So there are other bacteria which can either they can dampen the quorum sensing signal, or they can have quorum sensing mimics which can give a false impression to the bacteria that there are many more of its kind around. So these kind of interactions are there which are mediated through quorum sensing. So quorum sensing, in quorum sensing, a bacterium sends its signal outside, and the threshold level of that increases when its own population is high, right? And in that manner, when the threshold is high, it can sense it back, that molecule. So when other bacteria are there or other organisms can either dampen this signal by degrading these signal molecules, or they can enhance this signal by secreting mimics. So both possibilities are there. Any other questions? Sorry for overshooting. I'm sure you are waiting for the lunch. So, anybody has any other question? I'm there outside for some time. You can interact.
Thank you so much, ma'am, for your insight knowledge. Now there will be a lunch session, and after the lunch session there will be a poster presentation for postgraduate students upstairs. Okay.